Hi. In this video, we're going to be doing A-level for the Maths 9231, paper 24, for the pure Maths to October, November 2025. This paper is 2 hours long, and before we get started, I just want to let you guys know that if you're looking for one-to-one tutoring services for A-level maths, all components except statistics to paper 6, as well as all components for A-level further maths, please email me at the email address in the description. And I've also launched a channel membership where if you join, you will get unlimited access to all curated topicals for further maths for now. I'm gonna add more in the future, um, which has questions arranged in terms of difficulty, easy, medium, and hard, um, as well as the ability to get on a live call with me and ask me any question that you need help with. Yeah, so that's all. And yeah, with that, let's move on to the first question. Okay, so for the first question, we're told that I subscript n is this integral, where n is a non-negative integer. Okay, so for the first part, we need to show that for n more than or equals to 2 is this expression. Okay, so this is a classic reduction formula question. And for reduction formula, we always use integration by parts, okay? So let's do this for integration by parts as well. Okay, so let's start off with this integral. 1, 0, x to the power of n, shine x dx. Okay, so we have to use integration by parts here. So we should let x be u and shine x be dv dx. Okay, so doing that, this is u. V is therefore going to be cos x. So uv is x. Oh no. uv is x to the power of n cosine x 1, 0 minus v times du dx. So now we have to differentiate u as well. So doing that, we'll get n times x to the power of n minus 1 v, which is cos x dx. So this is 1, 0. Yeah, so let's evaluate this. Okay, so evaluating that, you'll just get cos 1. Yeah, you just get cos 1 minus n integral of x to the power of net n minus 1 times cosine x dx. Yeah, and yeah, as you can see, the resulting integral that we have, it's not in this form, right? So unfortunately, we would have to do integration by parts one more time. So just like before, this time x to the power of n minus 1 will be u, and cos x is going to be dv dx. Okay, so let's get started. Okay, I'm going to represent this using square brackets. All right, so u times v is going to be x to the power of n minus 1, and dv dx, integrate, you'll get v. So v is going to be sine x 1, 0 minus v times du dx. So du dx is just the integral, or the derivative of x to the power of n minus 1. So differentiating it is going to be n minus 1 times x to the power of n minus 2. And v is just sine x dx 1, 0. Yeah, so let's evaluate everything else. So cosh 1 minus n. Okay, so substituting 1 into here, 1 to the power of anything is 1. Shine 1, that's just shine 1. Minus 0, yeah, that's just zeros. Minus, remove the n minus 1. Integral of x to the power of n minus 2. Shine x dx. Yeah, so the resulting integral that we have from here, it perfectly fits this form, and therefore we can write it as I subscript n minus 2. Okay, so let's just expand everything out. Oh my goodness, what's going on? Yeah, let's just expand everything. So cosh 1 minus n shine 1 plus n times n minus 1, this integral, which is I subscript n minus 2. Okay, let's see. Yep, that is the exact form. Okay, so let me just put I subscript n. Yeah, so we can write shown here, right? So we can stop and move on to the next part. Okay, so for this part, we are just told to find I subscript 2. Okay, so to find that, let's just use the reduction formula that we derived. So I subscript 2 is going to be cosh 1 minus n shine 1, so 2 shine 1 plus n times n minus 1, so 2 times 2 minus 1, which is 1. I subscript 2 minus 2, which is just I subscript 0. Okay, so cosh 1 minus 2 shine 1 plus 2 I subscript 0. So I subscript 0 is integral of x to the power 0. That's just 1. So it's just the integral of shine x from 1 to 0. Yeah. Oh my goodness. What is this? Okay. Yeah. Yeah, so this, what's going on? Oh no. Just give me a while. Okay. Still not working. Yeah. Okay, yeah, now it's working. So it's saying I0 is just the integral of shine x from 0 to 1. Yeah, so yeah, just integrate that minus 2 shine 1 plus 2. So you're integrating shine x, you just get cosh x on 0. You get cosine 1 minus 2 shine 1 plus 2 cosh 1 minus cosh 0. So expanding it, you'll get 3 cosine 1 minus 2 shine 1 minus 2 cosh 0. So cosine 0, you'll get an exact value. Okay, so just type it into your calculator, go to hyperbolic functions. Yeah, you just get 1. So therefore, oh my gosh, why is it like this again? Okay, so therefore you just get 3 cosine 1 minus 2 sine 1 minus 2. Yeah, so I think we can stop here and conclude this as our final answer. Let's move on to the next question. Okay, so for the first part, we are told to find the exact values of x for which this equation is true, and our answer is supposed to be given in logarithmic form. Okay, so let's write down this equation here. So the first thing that I noticed about this equation is that they're not like in terms of the same hyperbolic function. So that's the first thing we should try to do. Okay. So I guess we can convert the cos 2x into um, sine square x. Okay. So yeah, sine square x, yeah, cos 2x, yeah, that's equals to cos square x plus sine square x. Okay. So cos square plus sine square x equals to 6 sine square x. Okay. Another thing that we can do is to separate the cos square and the sine square on the opposite sides of this equation, and then we can divide both sides by cos square x to get tangent square x. Okay, let's just stick to sine square x, okay? So now we have to change this cos square x into sine square x, and oh yeah, we can use this. Oh my gosh, okay. 1 plus sine square x plus sine square x equals to 6 sine square x. Okay, so moving all the sine square x's to the right hand side, you'll get 4 sine square x equals to 1. That would get you sine square x equals to 1 over 4, and sine x would therefore be square root of 1 over 4, both positive and negative, which is plus or minus 1.5. And the reason why we accept both negative and positive is because uh, the graph of sine x is something like this. Okay, so you can see like the range of x. It can be both positive. I mean, the range of sine x, it can be both positive and negative. So yeah, yeah. So this is gonna be our answer for sine x. Now we would have to find x. So x is obviously sine inverse half or sine inverse negative half. But the question told us to express it in logarithmic form, so let's find the expression for sine inverse x. So it's this right here, ln x plus x squared plus 1. Okay, so yeah, therefore this is going to be ln x, which is half, plus x squared plus 1. So x squared is 1 over 4 plus 1. So therefore, this would just be ln half plus 1 over 4 plus 1, that is 5 over 4. So square root 5 over 4 is square root 5 over 2. Same for this. This is going to be equals to ln negative half plus negative half squared. That's also 1 over 4 plus 1. So final answer for this would be ln negative half plus square root 5 over 2. Yeah, so this would be our two final answers for the first part. Let's move on to the next part. Okay, so for the second part, we are told to sketch the curves y equals cos 2x and y equals to sine square x on the same diagram. Okay, so let's draw axes. This is the x, this is the y. Okay, let's start off with C1 first, cos 2x. Okay, so to sketch cos 2x, let's start out by writing the exponential function, the exponential form. So for cos x, the general form is e to the power of x. So this e to the power of 2x plus e to the power of negative x, or in this case, negative 2x over 2. Now we're going to split this fraction up into two to give us two distinct functions. E to the power of 2x over 2 plus e to the power of negative 2x over 2. Okay, yeah, so now let's sketch this function first in dotted lines. So this function is almost like e to the power of x, so therefore it'll be something like this. Yeah, and as for this is almost the same as e to the power of negative x, so therefore it's gonna be like this. Yeah. And when you combine these two functions together, which is what we do to get cos x in general, your graph is going to look something like this. Yeah, so this is the graph for cos 2x or cos x in general. Okay, yeah, so I guess we can stop here for cos 2x. Let me just erase the dotted lines. Okay. Yeah, so the critical point for cos 2x would be 1, okay? The minimum point is always 1. So this is C1. And now let's do C2, sine square x. All right, so for sine square x, I think the best technique would be to use this identity for cos 2x. Cos 2x equals cos square x plus sine square x, okay? So yeah, cos 2x cos square plus sine square. So to only get sine square x, we're going to substitute the cos square x for sine square. So doing that, cos square, you just get 1 plus sine square. Therefore, this can also be equal to 1 plus 2 sine square x. Okay, and isolating 2 sine square x, you'll just get cos x minus 1. Okay, and to get C2 6 sine square x, um, you get that's also equals to 3 cos cosine 2x minus 3. Okay, so to sketch this, yeah, just sketch cos 2x first and stretch it vertically by the scale factor 3. Okay, so doing that, um, yeah, the maximum point would be, okay, actually, yeah, let me just shift C1 down a bit. Okay, so C1 is going to be something like this one, and C, um, 3 is going to be like more stretched out, so therefore it's going to be more like vertical. However, we can see that it's also minus 3, so therefore we shifted 3 units downwards. So therefore, minimum point is therefore going to be 0 for C2. Okay, yeah, so this is what C2 should look like, more squished because of the vertical stretch by scale factor 3, as well as the downward shift, the downward translation of 3 units. Okay, yeah, so yeah, I guess we can stop here for this part B. Let's move on to the next question. And okay, so for the first part of this question, we're told to use Lemav's theorem to show that this expression is true. Okay, so this is a very common question. So we are told to show that sine n theta is equals to these sum of this sum of the powers of sine. Okay, so to show that, we're going to start with this expression, cosine theta plus I sine theta, basically the trig form of the complex of a complex number. All right. So since we want to find sine 5 theta, we're going to raise this to 5 to the fifth power. Okay. So here's where Demav's theorem comes in. So Demav's theorem states that this power right here for this expression specifically, for this trig expression, we can we can distribute it over to the thetas. So therefore, doing that, the 5 will just be from the theta. So you'll get cos 5 theta plus I sine 5 theta. Okay. Yeah, so this is what Demav's theorem is. Okay, so to get the right-hand side of this expression, we're going to have to manually expand it out using binomial's theorem. So yeah, let's do that. Okay, so to expand this using binomial theorem, binomial expansion, you can use the formula in the MF19, but I'm just going to use the Pascal's triangle. Okay, so 1, 1, 1, 2, 1. So this for power 2, 1, 3, 3, 1 for power 3, 1, 4, 6, 4, 1 for power 4, and finally 1, 5, 10, 10, 5, 1. This for power 5. So these are all the coefficients of all the terms in our binomial expansion. Okay, yeah, so obviously the first term is going to be cos theta to the power 5 times 1. So it's going to be cosine to the power 5 theta plus 5 cosine to the power 4 theta times I sine theta plus 10 cosine cube theta times I sine theta squared. So the golden rule is to make sure that the power of cos theta and I sine theta, they always add up to 5. Okay. And the next term coefficient is 10. So 10 times cos square theta times I sine theta cubed plus 5 cosine theta times I sine theta to the power 4 plus finally I sine theta to the power 5. Yeah. So let's do it. Let's expand this out. So this is going to be cos 5 theta plus 5 I cosine to the power 4 theta sine theta plus 10 cos cube theta. So I sine theta squared, that's the same as I squared times sine squared theta. And you know that I squared is just -1, so therefore this is going to be minus sine squared theta. Okay, and then plus 10 sine square theta. Not sine, cos. Cos square theta. I sine theta cubed, so that's the same as I cubed sine cube theta. So I cubed is I squared times I. So I squared is -1. So therefore it's the same as negative I sine cube theta plus 5 cos theta. Okay, so I sine theta is the same as I to the power 4 sine to the power 4 theta. So I to the power 4 is I squared squared. So I squared is -1 and -1 squared is just 1. So this is just going to be sine to the power 4 theta plus I sine theta to the power 5. So that is just I to the power 5. So that's the same as I to the power 4 times I. And as you know, I to the power 4 is 1, so it's just I sine theta to the power 5. Okay, so now we're going to group all the real and imaginary terms separately. So let's group the real terms first. So the real terms are cos theta to the power 5 minus 10 cosine cube theta sine square theta plus 5 cos theta sine theta to the power 4 plus now let's group all the imaginary terms with I. So I 5 cos to the power 4 theta sine theta minus 10 cos square theta sine cube theta plus sine theta to the power 5. Yeah, so this is it. And now we're going to equate this expression that we use to find that we found using Demav's theorem and this expression using binomial. So since we're required to find sine 5 theta, we can see that sine 5 theta is in the imaginary part. Therefore, we're going to equate the imaginary parts of each of them to each other. Okay? So yeah, therefore, we get sine 5 theta equals to 5 cosine 4 theta sine theta minus 10 cos square theta sine cube theta plus sine of 5 theta. Okay, so one thing that we realize about the expression on the right-hand side is that everything is in terms of sine theta. So therefore, all the cos, we should change it to sine, okay? So to do that, we're going to express cos 4 theta as cos squared squared. And we know that cos squared is 1 minus sine squared. So therefore, this is just going to be 1 minus sine squared theta squared sine theta minus 10 sine cube theta. Cos squared is 1 minus sine squared plus sine to the power of 5 theta. Yeah, so doing that, you'll get 5 sine theta. So to expand this, so it's going to be 1 squared minus 2 times 1 times sine squared theta, 2 sine squared theta plus sine squared theta squared, which is sine 4 theta minus 10 sine cube theta plus 10 sine to the power 5 theta plus sine to the power 5 theta. Okay. Okay, so let's expand 5 sine theta minus 10 sine to the power 5 theta, and no sine cube theta, sorry, plus 5 sine to the power 5 theta minus 10 sine cube theta plus 11 sine to the 5 theta. Yeah, okay, so let's group all the sine to the power 5 theta terms first. So you get 16 sine to the power of 5 theta minus 20 sine cube theta plus 5 sine theta. So this is what sine 5 theta is equals to. Yeah, that is, yeah, it exactly matches. So yeah, we can write shown. Yeah, and with that, we can head on to the next part. All right, so for this question, we are told to hence obtain the roots of this equation in the form of sine q pi, where q is a rational number. So yeah, since we have the hence keyword, we obviously have to use our result from the previous part to solve this equation. All right, so yeah, let's first let yeah, so first we're going to substitute x equals to sine theta, because if only by doing that we'll be able to use this result that we obtained in here. Okay, yeah, so doing that you get 32 sine to the power 5 theta minus 40 sine cube theta plus 10 sine theta. Okay, let's move the square root 3 over to the other side. Yeah, equals to square root 3. Yeah, so let's look at the similarities of our result here and the equation that we have on the left-hand side. Okay, so all the powers are similar. The only difference is the coefficients. So you can see the coefficient for sine 5 theta here is 16, here's 32. Sine cube theta is negative 20, here's negative 40. And for sine theta, here's 5, and here is 10. Yeah, so it's just twice, okay? So we're just going to factor out 2 from here. So this will give us 2 times sine 5 theta minus 20 sine cube theta plus 5 sine theta goes to square root 3. So yeah, we can, this bracket expression, we can immediately just substitute sine 5 theta. Okay, so therefore 2 sine 5 theta, in this case, going to be square root 3 theta. Okay, so sine 5 theta is going to be square root 3 over 2. Okay, yeah. All right, so now let's solve for 5 theta. Okay, so yeah, just take out your calculator and type in sine inverse square root 3, square root 3 over 2. Make sure the calculator is in radian mode. So the first answer that we get is pi over 3. And remember that since the degree of this equation right here is 5, you're supposed to have 5 values of x, and therefore 5 values of theta, and as well, therefore 5 values of 5 theta as well. Okay, yeah. So yeah, to find the other value, yeah, you can use this unit circle here, A, S, T, C. So your sign's positive here as well as here. Yeah, so you can find any other corresponding angles in these two um, quadrants. Okay, so we found for the first quadrant. Now let's find for the second one. So second one is just pi minus pi over 3. So that's 2 over 3 pi. Okay, and the next one, we're just going to like add 2 pi to pi over 3. Okay, yeah, so adding 2 pi to pi over 3 for the first quadrant, uh, you'll get 7 over 3 pi. And now we'll add 2 pi to the angle in the second quadrant. So 2 pi plus 2 over 3 pi, you'll get 8 over 3 pi. And finally, we're going to add 4 pi to the first angle in the first quadrant. So adding 4 pi, yeah, will get us back here. So therefore 4 pi plus pi over 3, you'll get 13 over 3 pi. And to do one final check, see if they, when you take the sign of them, whether they give you square root 3 over 2. Okay? All right. So now we're ready to find what theta is. Theta is going to be pi over 15 for the first one, 2 over 15 pi, 7 over 15 pi, 8 over 15 pi, and finally 13 over 15 pi. So yeah, as you can see, all the values of theta, the coefficient of pi is all rational. So yeah, it fulfills this condition. So therefore, we can write down the values of x. So we know that x is sine theta, so we just have to substitute these values into sine theta. So therefore, we can say that x1 is sine pi over 15, x2 is sine 2 over 15 pi, x3 is sine 7 over 15 pi, x4 is sine 8 over 15 pi, and finally the last value of x5 is sine 13 over 15 pi. Yeah, so these would be our final answers for the second part as well as the entire question. Let's move on to the next question. Okay, so for this first part, we're given a diagram with this curve y equals to half 3 to the power of x for x between 0 and 1, together with a set of n rectangles which all have width 1 over n. Okay, so for the first part, we are told by considering the sum of the areas of these rectangles, we need to show that this integral, which if you don't realize is just the area under the curve from 0 to 1, is less than un, where un is equals to this expression. Okay, so yeah, so to find what un is, let's consider the sum of these rectangles. Okay, so you can see that all these rectangles, the top right-hand corner, it touches the curve, so therefore all of them are above the curve, and definitely if you sum up all of the areas, they're gonna be more than the area under the curve. Okay, so yeah, that's what UN is. It's the sum of all these rectangles shown here. Okay, yeah, so let's start by forming the inequality because we have to show that the inequality included. Okay, so this is going to be the sum of these rectangles. Each of them is 1 over n width. So the first one, the height is the y value when x equals to 1 over n. So therefore, this is going to be half 3 to the power of 1 over n. And the next one, you can see that it's the y value when x equals to 2 over n. So therefore, this is 1 half 3 to the power of 2 over n. And this is going to repeat all the way until x equals to 1. So yeah, we can write plus 1 over n, 2 times 3 to the power of n over n. So n over n is for consistency's sake. All right. Yeah. So yeah, this one we can rewrite. So this summation that we formed here, we can actually factor out some common terms. We can factor out 1 over 2n. And doing that, that just gives us 3 to the power of 1 over n plus 3 to the power of 2 over n, and so on, all the way until 3 to the power of n over n. Okay, so I want you to realize one thing. So you can see that all these terms, to get the next term, uh, Yeah, the numerator you just have to add one. So that's the same as adding 1 over n to the power of the previous term to get the power of the next term. Okay? And adding 1 over 1 to the power is the same as multiplying 3 times 1 over 1. Okay? So therefore, to get the next term, like of this sequence, you just have to multiply a certain number, which is a common ratio, which is 3 over 3 to the power of 1 over n. Okay. So therefore, all these terms here, they actually form a geometric series. And since they're all being added up, we can just use the sum of a geometric series. Okay. That are following a geometric series. Yeah. So, yeah. So to express that, we're just going to use the formula. Okay, let's go to the MF19, go to Pure Maths 1, just Pure Maths, sorry. So for geometric series, this is the formula for the sum of all terms in a geometric series. So A is the first term, and R is the common ratio, which is 3 to the power of 1 over n. Okay? Yeah, so it's that. So A is 3 to the power of 1 over n times 1 minus 1 minus r to the power of n, 1 minus r to the power of big N, because that's the number of terms we have, over 1 minus r squared. And no, just 1 minus r, sorry. Yeah, r is 3 to the power of 1 over n. Yeah, so this cancels. Okay, so this is 1, 0, half 3 to the power of x dx, 1 over 2n, 3 to the power of 1 over n. So yeah, canceling this power, you just get 3 to the power of 1. So therefore you get 1 minus 3, which is just minus 2 over 1 minus 3 to the power of 1 over n. So these, they cancel out. Okay, so let's see if there's any negative. Fortunately, there isn't. Okay, so we have to get rid of this negative somehow. I guess one way is to multiply both the numerator and denominator by -1. So doing that, it gives us 3 to the power of 1 over n times n minus n times 1 minus 3 to the power of 2n. But however, you can see there's no minus sign in front of the n. So therefore, you have to distribute it here, which will give us 3 to the power of 1 over n minus 1. And yeah, that is the exact form in there. So we can write shown in here. Yeah, so this would be our final answer for this first part. Let's move on to the next part. Okay, so now we're told to use a similar method to find in terms of big N, a lower bound Ln for this. Okay, so Ln is literally the opposite of Un, like the expression we found in the previous part. So Ln is obviously supposed to be less than this. So in other words, this integral right here is supposed to be more than L subscript big N. Yeah. So to do that, we just have to change the rectangles a bit. So now instead of the top left-hand corner of the rectangles, I'm sorry, the top right-hand corners, now the top left-hand corners will touch the curve for every single rectangle. Okay. So yeah, if you do that and you take the sum of all these rectangles that touch the curve in this manner, um, you're gonna get an area that is, less than the area under the curve. You can see there's like still some gap that's not covered by the rectangles under the curve. Okay? Yeah. So yeah, you can see that the height of the first rectangle is the y value when x equals to 0 over n, and the last one, the height is the y value when x equals to n minus 1 over n. Yeah. So yeah, this is therefore just going to be 1 over n times half 3 to the power of x. So the first one is 0 over n, and the next one is 1 over n half 3 to the power of 1 over n plus dot 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 1 over n half times 3 to the power of n minus 1 over n. Yeah, so yeah, this is going to be 1 over 2n. We factor out. Well, it's going to be 3 to the power of 0 over n plus 3 to the power of 1 over n plus all the way to 3 to the power of n minus 1 over n. So just like, the previous part, this series that we see here is a geometric series because to get the next term, you just add 1 over n to the existing power, which is the same as multiplying by 3 to the power of 1 over n to get the next term. And you add these terms up. So yeah, this is just the sum of a geometric series. So can use that formula. So it's a times 1 minus r to the power of n over 1 minus r, where r is the common ratio, n is the number of terms, and a is the first term. Okay, so therefore a, which is the first term, is just going to be 3 to the power of 0, which is 1. So 1 times 1 minus r to the power of n. So r is 3 to the power of 1 over n. And n is just big N because there's n terms, okay? Yeah, there's n terms in total, not n minus 1 over 1 minus r. 1 minus 3 to the power of 1 over n. Okay, so this cancels out, therefore you'll just have 1 minus 3. So this is 1 over 2n. 1 minus 3 is minus 2 over 1 minus 3 to the power of 1 over n. So the 2's, they cancel each other. And yeah, therefore you get 1 minus 1 over n times 1 minus 3 to the power of 1 over n. Yeah. So I guess we can stop here. And actually, yeah, I don't like the negative sign, so yeah, to get rid of it, let's just multiply both the numerator and the denominator by -1. So you get 1 over n times 3 to the power of 1 over n minus 1. Yeah, so yeah, this would be our final answer for this part. Let's move on to the last part. Okay, so for this last part, we are told by simplifying un minus ln, when you show that the limit as n approaches infinity of this is equals to 0. Okay, so let's find out what u subscript n minus l subscript n is. So u subscript n is that 3 to the power of 1 over n times 1 minus 3 to the power of 1 over n minus 1 over n times shoot. Sorry, I switched the terms. 3 to the power of 1 over n minus 1. Yeah, minus 1 over n 3 to the power of -1 minus 1. So this is 3 to the power of 1 over n minus 1 over n times 3 to the power of 1 over n minus 1. So yeah, they cancel out. Therefore, you'll just get 1 over n. And yeah, now we can find the limit of this 1 over n as n approaches infinity. So yeah, as n gets bigger and bigger, this will obviously just be 0. So therefore, we can say that the answer is 0 and right show. Yeah, so this would be all for this entire question. Let's move on to the next question. Okay, so for this first part of this question, we are told to find the general solution of this second order differential equation right here. Okay, so for any like second order, third order differential equation, the first step that you must do is to form the auxiliary equation. So to form that, you just look at the order of the derivatives. So for second derivatives, you just substitute lambda square in its place. For first order, you substitute lambda. And for non-derivatives like this, y, you just substitute the coefficient of that term, so which is 1. And the left-hand side, just ignore everything, substitute 0. Okay? And now you just solve for lambda. So I'm going to use the quadratic formula in here. So minus b is minus 1 plus minus square root of b squared. So b squared is 1 square minus 4 times a times c over 2 times 1. Yeah. So this is going to be minus 1 plus 1 square minus 4. That is square root negative 3 over, oh my goodness, over 2, and lambda equals to negative 1 minus square root negative 3 over 2. Okay, yeah, so as you can see, this we're not going to get real solutions here. So therefore, we're just going to split this up into two separate fractions to get minus half plus square root 3 over 2i. That's lambda 1. And lambda 2 is minus half minus square root 3 over 2i. Yeah, so these are our values of lambda. Okay, now we're going to find what y is. So now we're going to form something that's called the complementary function. So the complementary function is in this form: y equals to a times e to the power of your first lambda x, okay, depending on what you're differentiating with respect to. So lambda 1 is minus half plus square root 3 over 2i x plus b e to the power of negative half minus square root 3 over 2i to the power of x. Okay, so now let's expand this out. So y equals to a to the power of e to the power of minus half x plus square root 3 over 2ix plus b times e to the power of minus half x minus square root 3 over 2ix. Yeah, so now we're going to split the exponential. Now we're going to split e, okay? So splitting e, for the first one, we get a times e to the power of minus half x times e to the power of square root 3 over 2 ix plus b times e to the power of minus half x times e to the power of square root 3 over 2 ix. Yeah. Okay, so now we're going to expand this out using Euler's formula. So Euler's formula is e to the power of I theta equals to cos theta plus I sin theta. So we're going to use this. Okay. So doing that, you get y equals to a to the power of e minus half x cos square root 3 over 2x plus I sine square root 3 over 2x plus b times e to the power of negative half x times this is going to be cosine negative square root 3 over 2x plus I sine negative 3 over 2x. Yeah, so okay, so y equals to, and this is going to be a times e to the power of negative ex cos square root 3 over x plus a times I e to the power of negative half x sine square root 3 over 2x plus b times e to the power of half x. This here is the same as cosine square root 3 over 2x, and sine negative square root 3 over 2x is the same as minus sine square root 3 over 2x. So therefore, that's going to be b times I times e to the power of negative half x sine square root 3 over 2x. And after simplifying and all that, the final complementary function would just be y equals to c times e minus half x cos square root 3 over 2x plus d. Yeah, so the imaginary terms, they cancel out. So d e to the power of negative half x sine square root 3 over 2x. Yeah, so this would be the final answer for this part. I guess, no, it's not the final answer. It's just a complementary function. Yeah. Okay, so this is the CF. Yeah. Let's find the PI. Okay, so the particular integral, to find it, we're just going to let y be a function that is close to these functions on the right-hand side. So the function on the right-hand side, it's a trig function. All right, so obviously we have to equate y to this form. All right, so therefore y is just going to be equals to a random coefficient a sine 2x plus small b cosine 2x. Yeah. And now we're gonna find dy dx, which is 2a sine 2x. So cos 2x is just minus sine 2x. So this is gonna be minus 2b. No, this is supposed to be cosine, sorry. Minus 2b sine 2x and d square y over dx squared. This is going to be minus 4a sine 2x minus 4b cosine 2x. Yeah, so this is our expressions for y dy dx and d square y dx. Okay, yeah. So now, oh shoot, that's bad. Okay, Wow, why did they even give that much space? Okay, anyway, yeah, let's just add them up. Okay, so I'm just gonna group all the sines and cosines together. So minus 4a sine 2x minus 2b sine 2x plus a sine 2x plus b cos 2x plus 2a cos 2x minus 4b cosine 2x equals to sine 2x plus cosine 2x. So, how do I even? Oh, okay. Never mind. Yeah, so we can equate negative 3a minus 2b is equals to 1, and 2a minus 3b is also equals to 1. Okay, so yeah. Okay, let's just solve. Yeah, we're gonna let a be the subject here. So doing that, you get 1 plus 3b over 2. Substitute here, you get minus 3 times 1 plus 3b over 2 minus 2b equals to 1. Minus 3 over 2 times 1. Yeah, that's minus 3 over 2. Uh, minus 9 over 2b minus 2b equals to 1. And therefore b is going to be, oh my goodness, I can't believe I'm doing this. Man, okay. Minus 9 over 2 minus 2. Uh, negative 13 over 2. 1 plus 3 over 2. And negative 13 over 2. B is going to be minus 5 over 13. And A is going to be 1 plus 3 times negative 5 over 13 over 2 equals to 1 plus 3 times 5 over 13 divided by 2 minus 1 over 13. Yeah, so therefore our particular integral is y equals to negative 1 over 13 sine 2x minus 5 over 13 cosine 2x. And therefore, I'm just going to write the general solution here. The general solution is just a particular integral plus the complementary function. It is y equals to, oh my gosh, c times e to the power of negative half x cos square root 3 over 2 x plus d times e to the power of negative half x sine square root 3 over 2x minus 1 over 13 sine 2x minus 5 over 13 cos 2x. Yeah, so this is going to be our final answer for the first part. Let's move on to the next part. All right, so for this second part, we are told for large positive values of x and for any initial conditions, so the initial conditions don't matter, only the fact that the value of x has to be really large. We need to show that the solution to part A can be approximated by this expression where r and phi are positive constants to be determined. Okay, so first of all, let's find out what y would be approximately for large values of x. So in the general solution, as x gets larger, this e to the power of negative half x is going to approach zero. So is this. The rest, there's no definitive answer. So therefore, we can say that y would be, so therefore, c blah, 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 that's going to be zero. D blah, blah, blah is also going to be zero. So therefore, only this is going to remain. So therefore, y can be approximated to minus 1 over 13 sine 2x minus 5 over 13 cosine 2x. Yeah, so this is what y is. Now our only step remaining is to convert from this to this. Okay. Yeah. So to do that, this we have to do the R formula thing. Okay. So first steps for our formula is to expand out the initial expression given to us. Okay, so we're going to use the addition formula. Okay, so this is sine A minus B. So sine A minus B is sine A cos B minus cos A sine B. So this is going to be R sine A cos B minus R cos A sine B. Okay, so now we're gonna equate this this estimate to this. Okay, so this is square root 1 minus 13 sine 2x minus 5 over 13 cosine 2x equals to, oh my goodness, ayo, okay, equals to, ayo, seriously. Okay, let me just, equals to, oh my gosh, equals to, equals to r cos phi sine 2x minus r sine theta sine phi cos 2x. So by equating coefficients, we can tell that r cos phi is equals to negative 1 over 13 and r sine phi is 5 over 13. Okay, yeah, so now we can find out what tangent phi is. Tangent phi is just r sine phi over r cosine phi. So it's going to be 5 over 13 times negative 13, which is just minus 5. Okay, yeah. Okay, so they said that phi is positive. Okay, so okay, let's use the, so ASTC. So this is tangent with positive, tangent positive here. So phi has to be either here or here. Okay. All right, so phi is going to be tangent inverse negative 5. So to find phi here, it's just going to be pi minus tangent inverse negative 5. Pi minus tangent inverse 5, which is 1 plus 1.77 Yeah, 1.772 3 SF. Yeah. Yeah, and the reason why we chose this is so that phi, like we can choose the least possible value. Okay. And also it's positive. So this is where we get the least positive value. Yeah. And now to find R, we just use Pythagoras. We just square the R sine theta and we square the R cos theta. We add them up, we take the square root. So that is 26 over square root 26 over 13. Okay. So yeah, we found what y is. So y is approximately square root 26 over 13 sine 2x minus 1.77. Yeah, so this would be our final answer for this first part. Let's move on to the next question. Go ahead. Okay, so for this question, we are told to find the particular solution for this first order DE. And we're also given the initial conditions that when y is equals to pi, x equals to 0, and we're supposed to give our answer in an exact form. Okay, so to do this question, yeah, the coefficient of dy dx is 1, so we can immediately move on to finding the integrating factor. Okay, so to find it, you just take e and raise it to the power of the integral of the coefficient of y. Okay, so we have to integrate 1 plus x over 1 minus 2x minus x squared dx. Yeah, so yeah, to find this, um, we just okay. So we have to first integrate this. All right. So to integrate this, um, let's first check whether the denominator is factorizable or not. Okay. All right. So I'm just gonna check it. It's two minus one. Should minus one minus 2x. It is. Okay, but unfortunately, it doesn't have like um, whole number solutions, so therefore it's not factorizable. So we would have to complete the square for the denominator first. Okay, so yeah, let's start off by doing that. So let's factor out -1. So it's -1x squared plus 2x minus 1 dx. This is equals to 1 plus x over. Okay, now let's complete the square for this one. So to complete the square, you make sure the coefficient of x squared is 1, which it is. So you have x plus you take the coefficient of x, you divide it by 2, then you add it here. So this x plus 1, and you minus this number squared. So 1, and then you put the constant term at last, which is 1, which is minus 1. Okay, so yeah, let's bring back the negative sign. So this is going to be 1 plus x over 2 minus 1 plus x squared dx. Yeah, so this is the final integral, all right? So to solve this, let's take a look at what form this is the closest to in EMF 19. Okay, so you go to further pure maths 1, go to differentiation. So you can see that for sine inverse, cos inverse, tangent inverse, you get all these rational functions when you integrate. And we can see that this right here is the closest in form to our integral that we derived. Okay? Yeah, so I guess, yeah. And we get that form when we differentiate by a form of tangent inverse x, okay? So therefore, we're going to use integration by substitution. We're going to substitute square root tangent u equals to 1 plus x. And the reason why we put a square root 2 in front of the tanh u is so that when this gets squared, this would become 2 tanh square u, which would allow 2 to be factorized from this entire expression. Okay? Yeah. So now we're going to find out what dx du is. Okay, so dx over du is going to be square root 2. So differentiating tanh u, you'll get sec square u dx is going to be square root 2 sec square u du. Yeah. So yeah, now let's change everything to u. So this is going to be square root tanh u over 2 minus 2 tanh square u times square root 2 sec square u du. Okay, so let's do that. So 2 tanh u over, so you can factor out 2, so you get 2 times 1 minus tanh square u times sec square u du. So 1 minus tanh square u, you go to your hyperbolic functions. So to get an expression for that, we're just going to divide this expression by cos square on both sides. Then you get 1 minus tanh square x equals to 1 over cos square, which is sec square x. Okay, so yeah, 1 minus tanh square u is sec square u. So these two, they can cancel out, as well as this. Therefore, you only have the integral of tanh u. And to integrate tanh u is very simple. Just express tanh u as sine u over cosine u du. Yeah, so if you don't realize, this is actually in the form of f prime x over fx. So fx is cos u, and you differentiate cos u, get sine u. So therefore, you can express this as ln cosine u. So unfortunately, we're not done here yet. We have to bring everything back in terms of x, and the easiest way to do that is to express this ln cos u in terms of tanh. Okay, so to do that, we know that tanh u and sec square u, they are related. So we're going to express this ln cos u in terms of sec u. So this is actually the same as minus ln sec u. Yeah. And sec square u is minus ln square root 1 minus tanh square u. Yeah. Okay, so 1 minus tanh square u. So tanh square is... Okay, so let's go back to the substitution we made. So yeah, we can make tanh u the subject here. You would get x plus 1 over square root 2. Yeah. And tanh square u. Okay, I'm just going to do it here. Tanh square u is x plus 1 squared over 2. So therefore, this is going to be So I is therefore just going to be e to the power of minus ln square root of 1 minus x plus 1 squared over 2. Yeah. Okay, so let's simplify this. E to the power of that square root of 2 minus x squared plus 2x plus 1 goes to e to the power of negative 1 square root of 1 minus 2x minus x squared over 2. And this negative, we can move it over there. And this would be the power of negative. And by doing that, the numerator and denominator, they get flipped over. So this is therefore going to be e to the power of ln square root 2 over 1 minus 2x minus x squared. Yeah. And the e and ln will cancel. Therefore, this would just be square root 2 over 1 minus 2x minus x squared, the integrating factor. Okay, so now we can multiply this on both sides of the dE. All right, so doing that, we get square root 2 over 1 minus 2x minus x squared dy dx plus square root 2 over 1 minus 2x minus x squared times 1 plus x times 1 plus x over 1 minus 2x minus x squared times y equals to 1. So this one is just square root 2 over square root 1 minus 2x minus x squared. Okay, so let's differentiate this. Okay, so quite a lot of space. Okay, so we can express this as y times the coefficient of dy dx, which is this. It's going to be square root 2 over, okay, let's complete the square for this. Completed, the square is 2 minus x plus 1, 2 minus x plus 1 squared. Yeah, 2 minus x plus 1 squared. Yeah. And integrating these, I'm removing the dx. Oh my gosh, what am I doing? Y times square root 2 over 1 minus 2x minus x squared. You will get the integral of square root 2, 1 over square root of 2 minus x plus 1 squared dx. Yeah. So to integrate this, let's go back to our formula sheet. Okay, so let's see what integral this is the closest to. So it's a constant minus x. Constant minus x. Oh, it's just sine inverse x. So yeah, if it's close to sine inverse x, I guess we'll just substitute sine x for x plus 1. Okay. So yeah, therefore, I guess x plus 1 is going to be square root 2 sine u. And yeah, dx du is going to be square root 2 cosine u. And dx is going to be square root 2 cos u du. Yeah. Square root 2 integrate 1 over square root of 2 minus 2 sine square u times 2 cos u du. Okay, so you get square root 2 integrate 1 over factoring up to you get square root 2, then you get square root of 1 minus sine square. So 1 minus sine square is cos u, cos square u, square root, you'll get cosine u times square root 2 cos u du. So this cancels out. Therefore, you'll just get, oh shoot. Sorry about that. Yeah. So therefore, you just get square root 2 u plus, oh my god, plus c. Yeah, and then u would just be, well, why does it have to be like this, bro? Square root 2 sine inverse x plus 1 over square root 2 plus c. Yeah. Um, okay. Right. Okay, so let's just get into substituting the initial conditions. Y equals to pi and x equals to 0. Oh my gosh, y equals to pi and x equals to 0. So y equals to pi, you will get pi square root 2 over 1. Yeah, so it's just square root 2 equals to square root 2 sine inverse 0 plus 1 over square root 2. Square root 2 sine inverse 0 over square root 2 plus c. And then you will get c equals to, I guess it's sine inverse half is pi over 6. So therefore c is square root 2 pi minus square root 2 over 6 pi. So therefore c is, oh my gosh, c is c is 1 minus 1 over 6. Yeah, 5, oh my gosh, 5 over 6 square root 2 pi. Yeah, so this is c. Yeah, and therefore, yeah, we can conclude y square root 2 over 1 minus 2x minus x squared equals to square root 2 sine, I hate this, sine inverse x plus 1 over square root 2 plus 5 over 6 square root 2 pi. And if you want, you can simplify it to just y over square root 1 minus 2x minus x squared equals to sine, oh my gosh, sine inverse x plus 1 over square root 2 plus 5 over over 6 pi. Yeah, so this would be our final answer for this entire question. Let's move on to the next question. Okay, so I just realized that I made a silly mistake down there. Yeah, so it's supposed to be sine inverse 1 over square root 2, which is square root 2 over square root 2 over 4. Okay. Come on, please erase. Erase, come on. Okay, well, no, is this not working? Okay, never mind. I guess I'll just cancel. Yeah, so this is 4. Yeah, this 4. And yeah, C is therefore going to be 3 over 4. It's also going to be 3 over 4. Therefore, this is going to be plus 3 over 4 pi. Yeah, so this would be it for this question. Let's move on to the next question. Okay, so in this question, we're given these parametric equations for the curve C, and this is the range for t, where t is between pi over 3 and pi over 6. So for the first part, we have to show that dx dt is equals to this. Okay, so yeah, let's differentiate dx dt. They give so little space. So um, this is gonna be 8 uh, tangent half t. Oh my gosh, tangent half t, half secant square half t, minus 3, okay, cotangent t, to differentiate that, you get minus cosecant square c. So therefore, this is going to be plus cosecant square t minus 3. Yeah, so yeah, so all right. So simplifying this, you'll just secant square is 4 over cos square half t, and 1 over tangent square is cos half t sine half t. Okay, so this is, and then cosecant square t is okay, let's look at this. Okay, so it's 1 plus cotangent t. 1 plus cotangent, oh my gosh, cotangent square t. And then 3 is just 3. Okay. So this final expression we have is cos half t, sine half t for the first one. So if you realize that is very similar to the double angle formula for sine 2 theta, which is 2 sine A cos A. So we're manipulating it by adding a half. So 4 over half 2 cos half t sine 2t plus 3 3 plus plus oh wait, sorry, I forgot to include the 3. So there's 3 plus cotangent cotangent square t minus 3. So this gets cancelled. 4 over half, that is 8. So 8 over 2, yeah. So 8, so this is sine 2 half theta, so it's just sine t. So yeah, therefore 1 over sine t is 1 over cosecant t. Cosecant t plus, okay, this plus 3 cotangent square t. Yeah, so we can write shown here. Oh my God. Yeah, so this would be all for the first part. Let's move on to the next part where we have to find dy dt. Okay, so to find dy dt, yeah, let's differentiate that. So 6 ln. So it's almost the same form as this. So 6 half secant square half t over tangent half t plus 4 minus the this cosecant uh secant square t plus 4. Yeah. So yeah, we can simplify that. So this is gonna be 3 half sine t, 3 half sine t, and this is gonna be, oh my God, where does it have to 1 plus, so that's just minus 1 minus cotangent square t plus 4. So yeah, this cancels out. So this is going to be 6 cosecant t minus 4 cotangent square t. Yeah, so this will be all for the second part. Let's move on to the next part. Okay, so for this next part, we are told to find the exact value of the length of C. So they're telling us to find the arc length of C, okay? Yeah, so to find the arc length, we can use this formula for parametric equations. So it's the integral of the square root of dx dt plus dy over dt squared with respect to t, of course. And the length of this is pi over, so the limit is obviously pi over 3 and pi over 6. Yeah. So one way you can remember the arc length formula of parametric equations is that it's very similar to the Pythagoras um, formula, right? So it's x squared plus y squared, right? But you just replace the x with dx dt and the y with dy dt. Okay, yeah. So I just substitute everything in. So I'm just gonna make my handwriting a bit smaller. So dx, okay, so square root. So dx is 8 cosecant t plus plus 3 cotangent t squared. Cotangent squared plus oh my gosh, 6 cosecant t minus 4 co that was cotangent squared t squared dt. Okay, now let's square everything. So pi over 3, pi over 6. So squaring all that. So 8 cosecant t squared is 64 cosecant cosecant square t plus 8 times 3 times 2, that is 24. That's 48 cosecant, my gosh, cosecant cotangent square t, and then plus 3 cotangent square t squared, that is just 9 oh my gosh, co cotangent to the power of 4t plus 6 cosecant t, that is 36 cosecant square t minus 48. Oh my gosh, where does it have to be? Cosecant t cotangent square t plus 4 cotangent square t, which is 16 cotangent to the power of 4t. So yeah, this is cancelled, and pi over 3, pi over 6, square root 100, oh my gosh, 100 cosecant 100 cosecant square t plus 9 plus 16 is 25 cotangent t to the power of 4 t dt. Yeah. Okay, so now the next step is to substitute the cosecant square t for cotangent. Okay, so doing that. Oh my gosh, there isn't much space. Wonder. Okay, so doing that, you get, so cosecant square t is 1 plus cotangent square. So 100 plus 100 cotangent square t plus 25 cotangent 4t dt. Okay, so let's factor out 25. Okay, so factoring out 25. So you get square root 25, which is 5. And then we'll get cotangent for the power of 4t plus, what is this? Plus 4 cotangent square t plus 4. Okay. So in order to get rid of the square root, we have to express this in the form a plus b squared. Okay, so let's try to make this in the form a squared plus 2ab plus b squared. So according to this, b squared is 4, so b is going to be 2, and a squared is cotangent 4t, so a is going to be cotangent square t. Okay, and when you get 2ab, it's going to be 2 cotangent square t times 2, which is this middle term right here. So therefore, we can just immediately write, gosh, okay, let's put the 5 outside. We can immediately just write cotangent square t plus 2 dt. Yeah, we can write that. Cotangent square t. Let's see whether we can differentiate. Okay, we can't, so we have to use this. Yeah, using this, we can integrate minus cosecant square. Oh my God. Wow. It's a lot of steps. Pi over 3, pi over 6. So cotangent square is cosecant square minus 1. Cosecant square t minus 1 plus 2. So that's just plus 1 dt. Okay. Wow. Goodness. I'm just going to straight away integrate this. So this is therefore just going to be minus cotangent t plus t with the limits pi over 3 pi over 6. Yeah, let me do it here. So 5 substituting pi over 3, so 1 over tangent pi over 3, that's square root 3 over 3, so this is minus square root 3 over 3 plus pi over 3 minus negative cotangent t, so that's plus 1 over tangent pi over 6 is square root 3 uh, minus minus pi over 6. So simplifying and all that, after that you'll get 2 over 3 times 5, 10 over 3 square root 3. You'll get 10 over 3 square root 3 plus 5 over 6 pi. 3 minus 1 over 6. Yeah. Yep. So yeah, this would be the final answer for this part. Move on to the next part. Okay, so for this last part, we are told to show that the second derivative of this is in this form, where a, b, c, and n are integers to be determined. Okay, so to do this question, you have to first know the formula for the second derivative parametrically. So we know that the second derivative is d dx or dy dx, dy dx. However, we can't differentiate with respect to x, differentiate with respect to t. So replace the dx with dt, but that just changes the entire thing. So times dt dx, so that the value is the same, and multiplying by dt dx is the same as dividing by dx dt, divided by dx dt. Yeah. Okay. Right. So let's find what the derivative of dy dx is. So dy dx, that's just dy dt divided by dx dt. So essentially, we have to differentiate dy dt, which is 6 cosecant t minus 4 cotangent squared t over 8 cosecant t plus 3 cotangent t squared. Yeah. So to differentiate this, we use the quotient rule. All right. So we are going to square the denominator. God, squaring the denominator plus 3 cotangent t squared. Okay, so we keep the denominator. My God, keep the denominator plus 3 cotangent squared, and then we differentiate the numerator. Okay, so differentiating cosecant t is just minus cosecant x times cotangent x. So therefore, this is going to be minus 6 cosecant t cotangent x. Oh no, minus 4 2 uh, uh, okay, for 2, oh my god, 2 oh tangent t, oh my god, times differentiate cotangent is minus cosecant square. So therefore, this negative will be gone, and this will be cosecant square t. Yeah, and yeah, we should add it with the other set. It's going to be 8 cosecant t plus 3 cotangent squared t squared. Okay, so we keep the numerator this time. Yeah, we keep the numerator this time. Minus 4 cotangent squared t times the derivative of the denominator. So differentiating that 8 cosecant t. So differentiating cosecant x, it will be minus cosec x cotangent x. So minus, oh my god, minus 8 cosecant t cotangent t uh, plus 3 2 cotangent t. So differentiate tangent t, you'll just get minus cosecant square t. Yeah, all right. Now the next step is to factor out. Okay, so since we have cotangent cosecant t, we should factor that out. Okay, let's factor out 2 cotangent t, cosecant t from both. Okay, so doing that, you have, oh my god, cosecant t plus 3 cotangent squared uh, minus 6, not minus 6, sorry, minus 3 plus 8 cosecant square plus 8 cosecant square. Yeah. Cosecant square. Oh my god. Cosecant square. And since there's no like cotangent square in the numerator at all, we're going to replace the cotangent square with a cosecant square. So that's cosecant square minus 1. Oh my gosh. Cosecant square t minus 1. Okay, plus I'm just gonna combine the numerator. Okay, we can also factor out the tangent cosecant t from here. So doing that, we will get 6 cosecant t minus 4 cotangent square t, which we can also replace with uh, oh my gosh, cosecant square t minus 1 times minus 4 3 minus 4 minus 3 minus 3 cosecant cosecant oh my gosh, cosecant square t. Yeah. it is there any square? Wait. Huh. Wait. Shoot. Okay, I don't think there's any square. Oh, my bad. Yeah. All over the denominator. Cosecant t plus 3 cotangent square t. Okay. So after like expanding and simplifying, you will get to cotangent t cosecant t. Oh my gosh. 3. Oh my god. 3 cosecant square t minus 3 um, 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 plus 8 cosecant t minus 3 times 8 cosecant t minus 3 plus okay, let me put a square bracket here, plus uh minus 4 cosecant square t plus 6 cosecant t plus 4 minus 4 minus 3 cosecant t over 8 cosecant t plus 3 cotangent square t. Okay, so after expanding and simplifying, the numerator is just going to be 50 cotangent cosecant t, oh my gosh, times cosecant square t plus 1 over 8 cosecant t plus yeah, cotangent square t squared. So this is for dt equals to dy dx. So to get our final expression, you just divide by x. So yeah, divide by dx dt. Why does it always have to be like this? Cos 6 squared plus 1 over 8 cosecant t plus 3 cotangent squared t cubed. Yeah, so here we can show. Yeah, so oh my gosh, yeah, this would be our final answer for this last part was the entire question. Let's move on to the last question. Do this. All right, so for this first part, we need to find the set of values of A for which this system of equations has a unique solution, and we need to integrate this geometrically. Okay, so let's make this a matrix form. So 5A0, 20 minus 5, 0, 2 minus 3, 1, x, y, z, 3, 2, 1. Okay, so for this to have a unique solution, obviously, you're supposed to be able to take the inverse of this 3 by 3 matrix. And in order to take the inverse of this 3 by 3 matrix, the determinant of this matrix cannot be equals to 0. Okay, so first let's find the expression for the determinant. All right, so 5 minus 5, 0, minus 3, 1, minus a, minus here, minus a, 20, 0 to 1, and finally plus 0. Okay, I guess you can leave that alone, not equals to 0. Okay, so doing that, you got 5 minus 5 minus a, 20 minus 0, not equals to 0. And you'll get minus 20a. No, actually, let me just equate it to 0. Okay, that equals to 25. So therefore, a is going to be 5 minus 5 over 4. And therefore, we can say that a is not equals to minus 5 over 4. And now to interpret this geometrically, if this system of equations has a unique solution, there's only one possibility, is that all 3 planes intersect at the same at uh, at the same unique point. Oh my God. Yeah, so this would be the final answer for this question. Let's move on to the next part. Okay, so for this second part, we are told that given that a is equals to negative 5 over 4, which is the value found in the previous part, we need to show that the system of equations in part A is inconsistent, and we're supposed to give the geometric solution. Okay, so let's substitute it. So 5x minus 5 over 4y equals to 3, 20x minus, okay, so this is equation 1, 20x minus 5y equals to 2. And we can factor out 4. So doing that give us 5x minus 5 over 4y equals to 2. So this equation number 2. And you can see that equation 1 equation to the right hand side, they're just some scalar multiples of each other. Okay, so therefore that means those planes are actually parallel. But since the right hand side is not equal, they're not like the same planes, they're just parallel. Okay, and the last one is a completely unrelated plane, which has no relation to either of them. 3y plus z equals to 1. This is equation 3. So therefore, we can say that 2 parallel planes, other plane not parallel, other plane not parallel. Yeah. So now to prove that it's inconsistent, we're just going to substitute equation 1 into 2. Therefore, then you get 4 times 3 equals to 2, which would give you 12 equals to 2. So that's obviously not true, so therefore it's inconsistent. And the geometric solution would be 2 parallel, par two parallel lanes that are not equal, that are not equal. Two parallel lines that are not equal, and one plane that intersects both planes. So yeah, this will be the final answer for this part B. Let's move on to the last part. Okay, so for this last part, we're given this matrix A, and we're supposed to find matrix P and matrix D such that A plus 3i squared equals to PDP. Okay, so what the basic is telling us is to express this matrix in a diagonalizable form. Okay, so the matrix P is just the matrix that contains the eigen vectors of A plus 3i squared, and the matrix D is the diagonal matrix that contains the eigenvalues of A plus 3i squared. Okay, yeah, so first things first, let's find the eigenvectors and eigenvalues of A, right? So to find that, we have to find A minus lambda I. So doing that is 5 minus lambda, 0, 0, 20 minus 5 minus lambda, 0, 2 minus 3, 1 minus lambda. And now we're going to find the matrix, the characteristic equation. So the determinants of 5 minus lambda, 5 minus 5 minus lambda, 1 minus lambda, minus 0, 0, 0. Okay, good. So it's just 0. And now we're ready to solve. So therefore we get 5 minus lambda equals to 0, lambda 1 equals to 5, and minus 5 minus lambda equals to 0, and lambda 2 we get minus 5, and 1 minus lambda equals to 0, lambda 3 equals to 1. So these are the eigenvalues of these. Now we're going to find the corresponding eigenvectors, okay? So to find the eigenvector corresponding with the eigenvalue of 5, let's choose 2 rows that we're going to take the cross product of. So the condition is that those rows, they cannot be 0 rows or scalar rows of each other. Okay, so of 5, we're going to choose this and this because the first one is just going to be 0 row. So therefore, it's just going to be, let's just substitute it. 0, 0, 20, minus 10, 0, 2, minus 3, minus 6. Okay, yeah, so that's the matrix, and now we're going to okay, so so 20 minus 10, 0, 2 minus 3 minus 6. Yeah, so just use your calculator. Uh, so 5, 20 minus 10, 0. Vector 2 minus 3 minus 6. Vector A, vector B. All right, so you get 60, 120 minus 40. So you get 1, 2, and then you get 3, 4 minus 2. So it's the first eigenvector. All right. Okay, now let's do 4. So this was lambda equals to 5. Now we do 4. Lambda equals to -5. Okay. So we are going to choose this row, 20, 0, 0, and this row again. Okay. So by choosing that, you get 20, 0, 0, as well as 2 minus 3, 4. Okay. So okay, I'm just going to use my calculator. 20, 0, 0, 2, 2, negative 3, 4. Vector 3 times vector b, you get, oh my god, you get 0, negative 80, negative 60. So you get 0, so divide by negative 20 is 4, strict, negative 4, 3. Yeah, so this is the second eigenvector. Now let's do for the last case, where lambda is equals to 1. So to find the vector there, we're also going to choose like any two rows, right? So I think we can choose the same two rows. It's 20 minus 6, 0, 2, minus 3, 0. So doing that, okay, I'm just going to use 20 minus 6, 0, the 2, negative 3, 0, vector A, vector B, 0, 0, negative 4, 48. So we can, oh my god, what, negative 48, which is the same as 0, 0, 1. Okay, so yeah, these are the vectors, okay, of the eigenvectors, and so therefore we can find what P is. So P is just going to be these eigenvectors. The first one is 3, 4, minus 2. Second one is 0, 4, 3. Third one is 0, 0, 1. So this is P. And now we're going to find what D is, okay? So D is just A plus 3i. So what happens to the eigenvalue if you add Ni, okay, to the matrix is that the eigenvalues will also increase by 3. And if you also square them, if you square that matrix, the eigenvalue would therefore be squared. So therefore to get D, just have to take the existing eigenvalues. So the first one is 5. We add 3 and we just square it. Okay. So the next one is minus 5 plus 3 squared. And this one is 1 plus 3 squared. Yeah. So doing that, you will get 60, 64, 0, 0, 0, 4, 0, 0, 0, 16. Okay, yeah, so this would be all for P and D. All right, so again, if you want to get the eigenvalue for like this A plus 3i, okay? Given, the eigen value for the original matrix, you can take the eigenvalue of the original matrix, you add whatever the coefficient of I is, and if the existing matrix is squared and you want to find the eigen values of that, you just square the original eigenvalues of the original matrix. Okay. Yeah. Okay. So I just realized I made one mistake in here. Yeah. So I'm just gonna cancel. This is supposed to be minus minus 4, right? Um, yeah, so this here is supposed to be minus 4. Okay, let me see if I made any silly mistakes. Okay, this is supposed to be 6. Okay. Um, okay, let's see if I made any mistakes in here. So okay, all right. Okay, I'm just so yeah, just use your calculator to find them. Okay, 2, 3, 4. A times B. Okay, so you get 40. Oh my God, 40, 80, negative 40. So, oh my gosh, therefore, you get 1, 2, negative 1. So 1 to negative 1. Okay, and then for this, you're gonna get 20, 0, 0, and for the second one, you get 2, negative 3, 6. So you get negative 60, negative 60, negative 120, and negative 40. So therefore, this is 3, 6, and and wait, this is 3. I'm sorry, 3, 4, and 2. 3, 4, and 2. Yeah, and I think this is all right. Yeah, 0, 0, 1. So therefore, P is going to change as such: 1 to negative 1, 3, 4, 2, 0, 0, 1. Yeah. So this would be our answer for P. Okay. And yeah, we have also come to the end of this paper. So I hope you found this video helpful. If you did, please make sure to like and subscribe for more future A-level math and further math content. If you have any questions, queries, or doubts, please feel free to leave them in the comments below. And I'll see you guys again next time. Okay, thank you.